Hello students, in this video we will prove the variational principles. Okay, now we suppose that we wish to calculate the ground state energy Eg of a system with the Hamiltonian H. Okay, this Hamiltonian is known and we cannot solve this Hamiltonian as exactly. Okay, while the wave functions are arbitrary, or we can say that the wave function is unknowns. Okay, now to prove this variation principle, let us consider if the psi is any arbitrary normalized wave functions, like psi is equal to summation n and cn and psi n. Okay, this is any arbitrary wave functions though. Okay, and where the psi n is or the eigenfunction of h. Okay, this is the eigenfunction of h, to which form a complete set, and h and psi n and e n is equal to e n and psi n. Okay, okay, now the normalization condition for this arbitrary wave functions is this is equal to 1 of the expectation of the psi and the psi. Okay, then we put the value of the psi, then this is summation, and this is for state m. Okay, and cm and psi m, and then summations n and cn and psi n's. Okay, now here the cm and the cn as constants, then we will take outside this, and this is summation m, summation n, and cm steric and cn, and then psi m and psi n's. Okay, okay, now when the m is equal to n, this is a canonical delta we're using here, then this equations, the summation n, only one summations. Okay, and then this is psi cn steric and cn and psi n and psi n's. Okay, now this according to normalization condition, this has become ones. Okay, and then the summation of n, and this is the mod of x. Okay, this is equal to ones. Okay, okay, now if we take the expectation of the Hamiltonian with this arbitrary functions, okay, the psi n with the psi, then the expectations of h is equal to the psi and to h and to psi. Okay, this is the expectations of h. Now we put the value of psi, then this is summation of m and cm and psi m and h, and then the summations of n and this is m. Okay, this n and this is psi n's. Okay, then we outside this constants, summation m, summation n, and cm steric and cn. Okay, and then the psi m and h of psi n's. Okay, when the psi n is a fly and the psi n, then this is a en and psi n's. Okay, they form a complete set. Okay, then summations m, summation n, and cm steric and cn and then this E is constant, then this outside test, okay, and then psi m and psi n, okay. Now when the m is equal to n, then again this is sum of n, and this is Cn stack, Cn and En, and this is psi n and psi n, okay. Now according to the normalization condition, this is become 1s, okay. Then summation of n, and this is become mod Cn mod and En, okay. Since the ground state energy must be the smallest eigenvalue of the Hamiltonians, okay, the ground state energy must be less than or equal to the eigenvalue of the Hamiltonians, okay, as the Ens, okay. Then and the expectations of H, okay, is greater than or equal to the ground state energy and the summation of n and C mod n square, okay. We know the value of this is equal to 1s, okay. We have already discussed the H video is equal to 1s, okay. Then we can write these equations equation like here, okay. Then this is approximately is equal to the ground states, okay. And this is called the variational principle, which allow us to commute in the upper bound on the ground state energy, okay. But in the practice, this means we minimize the value of the Hamiltonian expectations value to achieve this upper bounds, okay. Then we take the expectations of this Hamiltonian to find the upper bound, okay, to the ground states, and this is approximately is equal to the Earth's ground state energy, okay. This is let's say this is the ground state. Then when we minimize this Hamiltonian with respect to the adjustable parameters, okay, then this is a minimum value to this ground state. Let's say this is 1 and this is 2. This value, okay, this is a minimum value to the this ground states. So X will give this minimum value to the ground state. There is approximately, or we can say, are higher than this, okay. Thank you.